Welcome to the last asynchronous video for this week. Congratulations for reaching up to here. The last thing that remains for this week is the addition of binary numbers and the subtraction of binary numbers. So, binary addition is carried out exactly the same way as you are used to in the decimal system. This is the very good news, and there is actually even better. Since there are only 2 digits, then the addition tables are much simpler. But let's be a little bit careful here. 0 plus 0 obviously gives you 0. 0 plus 1, and of course 1 plus 0 gives you 1. But as exactly you would do in the case of the decimal system, 1 plus 1, well, you need to come up with a rule here, because you got a sort of an overflow. 1 plus 1 we define it as 0, and we carry the extra 1 to the next column. So things will be more clear to you if we focus in this small example that you got now on the screen, when you try to add 13 to 11. Now let's convert them first in binary format. When you do that, you will realize that 13 is represented as 1101, and of course 11 as 1011. I'm not going to do that now, but based on the previous videos, you should be now in the position of doing it by continuously dividing by 2 and so forth. Now let's apply the above addition tables to this simple addition. Let's start from the rightmost bits towards the most significant bits. So from the least significant ones, 1s plus 1, well, that falls to the rule over here. The result that you get is 0, and you carry 1 to the next column. So that means 1 plus 0, which gives you 1, plus 1, okay. Then again you fall into this rule that you need to carry 1 on the other side. So you put 0 here, and then you go to the left column. 0 plus 1 equals 1, plus what is carried from previously, that gives you 0, plus you need to carry to the next column another 1. 1 plus 1, well, this means you need to carry something over here, plus what you carried earlier on. This gives you 0 plus 1 equal to 1. And then you realize that you need another bit here. So implicitly it's like saying 0 plus 0, which would give you 0, plus 1, that gives you 1. Now, by now you should be all familiar with this process, because this is what you've been using since a very young age for the decimal system. So addition in the binary system is very, very easy, as long as you remember this very, very simple rule when it comes to 1 plus 1. In this case, you just need to carry 1 to the left column. And obviously the result here is number 24. You can verify that by using the summation rule we've shown previously. Now imagine that there is this circuit that does the addition. What you need to have is the first bit that comes in, the second bit that comes in, and you also need another input, which is the carry in. And apart from the sum that comes out, you need another output, which is the carry out to the next column. Now, this implements what you see over here in this sort of a truth table, where you got all the possible combinations. 0 plus 0 plus whatever it's carried as 0 gives you a sum of 0 and nothing to carry out. And so forth. Perhaps the most the case that is worth referring to the most is this final one over here, when it happens that you need to add 1 to 1 and you also carry in from previously another 1. Well, the result in this case is 0 from 1 plus 1, plus 1 that is carried previously. It gives you a final result 1. However, you also need to carry out to the next adder another 1 over here. if you want to take a look at this table a little bit more, at this point I propose that you pause the video and you take a careful look. Now, if you have this small building block over here that just adds 2 bits, the only thing you need to do in order to create a multi-bit adder is to connect the carryout from the one building block as input to the next. And by working like this chain over here from the least significant bits towards the most significant ones, that every time you carry out something and you put it as a carry into the next column, then you end up in this multi-bit adder. Now, there's one thing over here, that the final adder, if it has a carryout, then this means that you are out of range. Well, oops, in this case it means that you didn't have enough bits to represent your number in binary format. This is something that you will learn during your studies, that it's the notorious buffer overflow case. Unfortunately, if you don't have enough bits, then in this case the result will not be right. And there are ways, of course, to deal with that, but this is not the time to discuss them. Now let us proceed with the subtraction of binary numbers. Again, things are easy because we're dealing with only 2 states, 0 and 1. The only highlight is the case that you're trying to subtract 1 from 0. In this case, the result is defined by 1 as 1. However, you need to borrow 1 from the next column. Now, notice the equivalence here. When you were adding numbers, you would carry 1 to the next column, to the more significant bits. In this case, you are proactively subtracting or borrowing 1 from the next more significant bits on the left column. In order to grasp better this, let's showcase it with 2 simple examples. The first one is when you try to subtract 11 from 13. Here's what happens. You start with nothing being borrowed, of course, because this is your first subtraction. So it's 1 minus 1, and the result is obviously 0. However, you quickly fall into this case where you need to carry 1 from the next column, because 0 minus 1 gives you 1, but you need to borrow something from here. So when you have borrowed it, this effectively means that you've turned this 1 over here to 0. So this is equivalent to the case of 0 minus 0 equal to 0. And then 1 minus 1 gives 0 over here. And this is how you get number 2 as a result. Now let's see a slightly different example. Again, we apply the same rules. You have previously not borrowed from this column, so you go straight to the case where you subtract 1 from 0, and that gives you as a result 1. However, you need to borrow 1 from the left column. Nevertheless, in this particular case, there is nothing to borrow because there was previously 0 here. So what happens is that you need to borrow that from the column on the left. Well, you don't have that, so recursively it's like borrowing it from the column on the left. So going back to here, 0 minus 1, you need to borrow 1 from the left, which would make it a 0 as a result here. Then you go over here, you already need to borrow 1 from the other column because you don't have it, so you borrow it and you make it 1 minus 1 equals 0. And then you go to the leftmost column where effectively this has turned into a 0 because you've already borrowed it from the subtraction that preceded it. And the result is, of course, 0 minus 0 equals 0. Now, let's go through that example again because it's interesting. What makes it interesting is that we tried to borrow from a column that didn't have anything that we could borrow from. So that created a chain of borrowing. Let's look at it again. 0 minus 1, you need to borrow 1 from the left column. Let's assume that you had that for now. So that would effectively make that 1 minus, sorry, that would effectively make it 1 over here as a result, as we know from the rule. And when you reach here, well, it's like you've borrowed 1, so it's, but you didn't have it. So effectively, you need to borrow it from the left column. Now assume now that you could borrow it. That would make it 1 minus 1 equal to 0. And then you reach here that you see like you had to borrow 1, which you never had. So you need to borrow it from the left column. So in this case, this makes it 1 minus 1 equal to 0. And now when reaching to the most significant bits, that 1 over here was already borrowed. So effectively now that is equal to 0. So it's 0 minus 0, which gives you a 0 as a result. Now, in case you find it a little bit difficult to understand these examples, I would suggest that you try to do some normal subtractions that you're used to with a decimal system, and then try to adopt the same logic to the binary system. The only rule you need to remember in the binary system is that when you try to subtract 1 from 0, then the result should be 1, and you need to borrow proactively something from the next column. And to wrap up, in this slide, this final slide for the asynchronous videos of this week, we show the binary subtraction implementation. Now, if this is a subtraction unit, it needs to get x and y as its input so that it gets out a result of d equals x minus y. And of course, you need another input, the binary in, sorry, the borrow in, and you need another output for the borrow out. Now, this is the table with all the possible combinations. Perhaps the highlight is this last case, but not only that, there are other highlights. Of course, you need to go through the table row by row. I suggest that you pause the video and you do that right now. But notice especially those 2 rows over here and the final row over here. This is how you will understand the meaning of borrowing from the next column. Now, to conclude, obviously, if you want to have a multi-bit subtractor, just like we previously explained for the case of the multi-bit adder, you need to change the borrow out from the previous less significant bit subtraction to the borrowing of the next subtraction, of the next more significant bits, the ones on the left column, and so forth. As a final comment, there is another way to do a subtraction. As you know also from the decimal system, a subtraction is equivalent to adding to a number a negative number. So one way is just to negate the subtrahend and proceed with an addition, which has a lot of advantages, but that is another story to tell during next week.